Okay, folks, in this particular video, we are going to look at the idea of how to do different selections here when your items have more than one characteristic, and no more perfect example than a deck of cards, because cards have different attributes to them, such as the suit, such as the rank, such as being a face card, etc. And when we do that, we're going to kind of mix our strategies here and look at this as a cross between a fundamental counting problem, but we're going to need to maybe use some different techniques to efficiently get the answer. Okay, so let's examine this first opportunity here where it comes to counting the face cards. So you're going to shuffle up a deck of cards, a standard deck of 52, and you're going to give yourself 5 cards. And you want to know how many hands have only face cards. How many ways can you deliver yourself only face cards? So you know you're going to get 5 different cards here. So it's kind of like a fundamental counting problem because you're looking at the number of ways that you can get 5 different face cards here. Okay, great, fantastic. All right, well, if they are only face cards, then this is where we're going to have to think about this a little bit more carefully here. Okay, so we know that all of these are face cards. Okay, we know that for sure. So if we're interested in drawing face cards, then I am only interested in the 12 face cards that there are that are in the deck. I'm only interested in just those 12. So Jack, Queen, and King in each of 4 suits, that's 12 face cards. And I want any 5 of them. So we have 12 face cards, and you want any 5 of those to occupy your hand. Okay, well, how would you figure that out? Well, you would take the number of combinations of 12 face cards, taken 5 at a time. Now, why would we use combinations here? Because it really doesn't matter the order in which you get specific cards. It just matters that they're all face cards. So I'm going to do combinations of 12, choose 5. That ends up being 792 according to my calculator. So there are 792 different hands that are available that contain all face cards. That's kind of an interesting problem to look at here. Now, I want you to note that I didn't really pay any attention to the other cards in the deck. I was not interested in anything if it wasn't a face card. And that makes a lot of sense here. So the other 40 cards I just was not even worried about because I was just trying to select cards that were face cards. Okay, let's take a look at this next example here and how many have hands that have exactly 2 hearts. Well, let's draw our blanks here to kind of help us organize our information. We're going to get 5 cards. And we know for a fact that 2 of these cards, that's a crummy looking heart. Let's try that again. Okay, a little bit better. Still crummy. Not happy with that one. Let's try this one. All right, that's a little bit better. So you have 2 cards that are going to be hearts. And the thing that you know that's important here is that these other 3 remaining cards, the one thing you know is that they are not going to be hearts. Okay, now why is that the case? Well, think about it. If your hand has exactly 2 hearts, then the other 3 cards must be spades, diamonds, or clubs. And that's something to consider very carefully here. These are really tricky problems, and they pack a punch in a very short amount of words, but at the same time, they are important to know how to do here. Okay, well, how do you choose the hearts? Let's choose this one at a time. Let's select the hearts, and then let's worry about the cards that aren't hearts. To select the hearts, there are 13 in the deck, and you want 2 of them. Okay? Now, again, we're focusing on just the hearts themselves in that particular part of the problem. Now, for the cards that aren't hearts, I'm going to select from the 39 cards that are not hearts in the deck. And I'm going to pick any 3 of those. Okay? All right, and then when I'm all said and done here, I'm going to multiply those numbers together. So 13 choose 2, according to the calculator, is 78. And 39 choose 3, according to the calculator, is 9,139. So there are 78 ways to select 2 hearts. There's 9,139 ways to select the 3 cards that are not hearts. And what I shall do is multiply those numbers together, because ultimately this is a fundamental counting problem. So you have to make your selection for the hearts, make your selection for the cards that aren't hearts, and multiply those two together. And when you do, you're going to get a big number. You're going to get 712,842 different hands that have hearts in them. 2 hearts, specifically. Okay, so that takes care of that problem. Let's move on to C here, which says how many hands have all cards of the same suit. All right, well, sometimes in mathematics, it's a little bit easier to think about a specific problem than it is a more general one. And this is a more general one because it doesn't specify which suit you are interested in. Okay? It doesn't specify which suit you're interested in. So let's just consider the case where you want all of these cards to be clubs. Okay, you want all 5 of those to be clubs. Well, how would you select the clubs out of a deck? Well, there's 13, and you're going to pick any 5 of them because you're not interested in any other suit. You want all of these to match, is what you want. And that number is going to be 1,287. Okay, now this makes a lot of sense for one particular suit, but the problem is all cards of the same suit. So I could repeat this problem for the remaining suits, or I could do this a little bit more smartly. Let's think about this here. If I did this for clubs, it should be 1287. But think about this. If I change this qualifier from clubs to hearts, well, it's still 13 hearts, and you're going to pick 5. That's still 1287. Change this to diamonds. You're still going to get 1287. Change this to spades. You're still going to get 1287. So what we really have here is we have to account for the different choices of suit. So I'm going to take that 1287 and multiply it by 4 choices of suit here. And that's going to give me 5,148 hands that have all of the same suit. Okay. All right, so let's kind of combine our concepts here for this last problem on this panel. 3 cards belong in one suit and 2 in another. Okay, so let's, again, get a really specific case here. So here is my 5-card hand, and I'm going to say that I have 3 cards. Boy, that's a terrible looking spade. Let's just not even try to do the glyph here. Let's just try to go ahead and do the writing. That might be better. Okay, so 3 cards will be spades, and let's just say that 2 cards will be diamonds. Okay. Now, again, this is kind of like looking at a specific problem first to solve a more general one. All right, well, for the spades, there are 13 in the deck. I'm going to choose 3. For the diamonds, there are 13 in the deck, and I'm going to choose 2. All right, so there's that setup. Now, here's the problem, though. We said 3 cards will be of one suit, and 2 will be of another. So how many choices do you have for this first suit of 3 cards? Well, you actually have 4 choices of suit for those particular spades. So I'm going to multiply those by 4 is what I'm going to do over here. Now, once you've selected the 3-card suit, now you've got to go and select the 2-card suit. And you can't use the same suit twice. So here you have 3 choices of suit. So I'm going to multiply that by 3 as well. So what I have here is I have 4. Let me get this in my calculator real quick here. I have 4 times the number of combinations of 13 items taken 3 at a time, and then multiply that by 3, and then multiply that by another combination of 13 and 2. Okay, now here's the magic number here. We end up with 267,696 different hands that have 3 cards of one suit and 2 of another. Interesting, interesting. Let's go on to the next one here. Okay, slightly different situation here. We have 7 rotten apples that are in a crate of 26. That reminds me of a geometry class I had a long time. Okay, shouldn't say that. I'll be nice. So 7 rotten apples that are in a crate of 26. Interesting, interesting. Okay, so we've got this crate of apples here, and we have 7 that are rotten. Okay, now stop and think for just a moment here. That means we have 19 that are good. Okay? So we have 19 good apples and 7 rotten ones that are in a crate full of 26. All right, so let's see if we can do some counting on this one. How many samples of 3 apples can be drawn from the crate? All right, now I want to point out something really interesting here. Reread the question. How many samples of 3 apples can be drawn from the crate? This question never says anything about the apples being good or rotten. They just say it's coming up from the crate. Okay, so we've got our samples of 3. So I can pick from the 26 that are in there, I can pick any 3 apples. Doesn't matter if they're good or rotten, just so long as I just pick any 3 of those. All right, now just for the sake of information, that's 2,600 different ways. I don't know how it worked out that cleanly, but it did. Okay. All right, now, second question. How many samples of 3 could be drawn in which all 3 are rotten? Okay, so if all 3 are rotten, I am not interested in any of these that are good. I only want to draw the rotten ones out. And there are 7 rotten ones, and I'm just going to pick any 3 of those. So that is going to be, let's figure out what that is really quick here. That's going to give me 35 different ways that I can select 3 rotten apples. Okay, question C. How many samples could be drawn in which there are 2 good ones and 1 rotten one? Okay, so let's kind of fill in our blanks here. So we're going to pick 3 apples. These 2 are good. This one is rotten. Okay, so let's figure out the number of ways that we can choose the good ones. There are 19 good ones. I'm going to pick any 2 of them. And then for the rotten ones, there are 7, and I'm just going to pick any one of those to fill my selection of 3 apples. So let me go ahead and get the number of combinations of 19, choose 2, multiply by the number of combinations of 7, choose 1, and you should end up with 1,197. All right, one more type of problem here. Let's see if we can get through one more. All right. So in an experiment on plant hardiness, a researcher gathers 6 wheat, 3 barley, 2 rye. And she's going to pick 4 plants at random. Okay, so let's kind of color code this to make this a little bit easier. 6 wheat and 3 barley, and then 2 rye. So by my count, 6, 3, and 2, that is going to be a total of 11 plants. Okay, now part A says, How many ways can she select? 4. All right, so for part A, it's 11, choose 4. Now, why is it 11 and not breaking it down by type? Because the question never said anything about breaking it down by type. We're only focused on, hey, there's 11 total. Even though the breakdown is 6, 3, and 2, you're not really worried about that right now. Okay, let's go on to part B here, which says, in how many ways can this be done if exactly 2 wheat plants must be included? All right, so let's set up our blanks one more time. We're going to pick 4. And we know that 2 of these must be wheat. So what do we know about these remaining plants? Well, they cannot be wheat plants. Okay? If exactly 2 are wheat, we didn't put any restrictions on the others other than to say they're just not wheat plants. So, let's figure out real quick what that's going to be. Combinations of 6, choose 2 for the wheat plants. Now, this is where things get a little bit interesting, because how many plants are there that aren't wheat? Well, there's 3 barley and 2 rye, so that's a total of 5. And I'm going to pick any 2 of those. And I'm going to multiply that result together in order to come up with an answer here. So let me go ahead and get that figured out. And give me just a hot second here as I work on my calculator to get this done. So combinations of 6, choose 2, and multiplied by 5, choose 2, you're going to get 150. I guess we really didn't get a number for 11, choose 4, so I'm going to go ahead and do that really quick here. Just so you know what it is, and maybe you'll sleep better at night knowing it's 330. Okay. All right, folks, this is a very fascinating thing to try to figure out the number of selections when things have multiple characteristics. Enjoy.